Hey everyone, it's Miss List. We're here with 5.4, which is on elementary reactions. You might not be aware of this, but reactions often don't occur instantaneously. They occur in a series of steps. And in chemistry, we call this a mechanism, sometimes referred to as a reaction mechanism. Well, an elementary reaction is a single step within the mechanism. So, for example, we have this reaction where I have 2NO reacting with one oxygen molecule to produce two NO2 molecules. So the way to think about this is I have two NOs, right? So I have two NO molecules and I'm colliding it, or a collision has to occur between the two NOs and the oxygen, and that's going to produce two particles or molecules. Now, it is very unlikely for all three particles to collide at the same time and in the correct orientation for a reaction to occur. And so this doesn't happen all at one time. It would be like three people trying to high five at the same time. You just have to make sure that everything is lined up. You have to make sure that you go at the same time. And when you have two reactants colliding with a third reactant, that makes it really challenging. So this reaction is an example of one that occurs in a series of steps. So step one, the two NO molecules will collide together and they will form in what's called an intermediate into O2. And this intermediate is super unstable. And so once the intermediate is formed, then the intermediate is going to react with the oxygen to form the two NO2 molecules. So this would be step two of the reaction. The term intermediate is something we use to describe a species that isn't a reactant or a product. So in the original equation, we didn't see N2O2 at all. And that's what makes it an intermediate. It's something that gets produced and then immediately used up in a later step. So the net equation that we look at in this mechanism would cancel the intermediate out. So here I have step one, that was the two NO molecules colliding together to form the unstable intermediate. And then in step two, the unstable intermediate reacts with oxygen. But like I said, the intermediate does not appear in our overall reaction. So these are two elementary steps. So that will add up to the overall reaction. And again, we're canceling out that intermediate. The intermediate does not appear anywhere in this mechanism or in the overall reaction. Now, how did we know that this process happened? Well, we did lots of studies. We paused the reaction at different points in time and analyzed what was in the mixture. And we saw that this N2O2 appears and then disappears again. And so this is done over lots of lab experiments to figure out what is going on in this mechanism. How are the steps working to add up to what we eventually see? Molecularity is a vocabulary term that describes the number of molecules that must collide in an elementary step. So in each of the elementary steps that we looked at, they would be considered bimolecular because they have two things colliding. In a decomposition reaction, that might be unimolecular because there's only one particle. And that might also include a nuclear decay. Termolecular is three colliding particles. And again, these are very rare because it's highly unlikely for the three particles to collide with enough energy and in the proper orientation like we talked about in 5.1. Those are the things that have to happen: collisions, enough energy, and orientations. And so termolecular reactions are very rare. The rate law can be inferred from an elementary step based on the number of molecules that collide. For example, and when we looked at our rate law, or the example above, our rate law can be inferred as rate equals K to the NO2 because there were two particles of NO that must be colliding. The rate law for step 2 only, and this isn't for the overall reaction, this is only for an elementary step. So the rate law for an individual step is what we're talking about. And we can look at the rate law for step 2 would be that the N2O2 and the O2 have to collide. And so these would be individual rate laws for elementary steps, not for the overall reaction. So let's look at some examples and see if we can suss this out. A possible reaction mechanism for the conversion of ozone to O2 is shown below. And so the first question is they want us to identify the molecularity of each step. So the first thing they want us to do is to identify the molecularity of each step. Remember, molecularity is just identifying how many molecules are colliding. So for step 1, that's unimolecular because there is only one reactant, and that's the O3. But in step 2, we have two particles. O3 is reacting with an oxygen, a single oxygen, and that's actually called an oxygen radical. We're not going to talk too much about what radicals are, but just so you know, that can happen. It's not an error. But this would be considered bimolecular because I have the ozone reacting with an oxygen radical, so two components in that elementary step. The overall reaction, they want us to cancel out anything that would be an intermediate. So again, an intermediate would get produced in one step, but then used up in a later step. So to me, it looks like the oxygen radical gets produced in step 1, it's a product, and then in step 2, it's a reactant. And so that is going to be my intermediate. And they want us to explain in part C, it gets produced in step 1 and used up in step 2. So when we write the overall equation, we cancel out that intermediate step, just like we've seen in net ionic equations where we cancel something on both sides. So now I rewrite what's left over, and I have two ozones, one here and one here. So that's going to be two ozone particles are going to produce one oxygen plus two more oxygens. So that would be 3 O2 gas particles. There you go. Our second example says nitrous oxide N2O is believed to decompose in a two-step mechanism and it's shown below. So I have step 1 is N2O is decomposing to N2 and O. And again, that's that oxygen radical. And then it looks like that oxygen radical gets used up in the next step. So that appears to be my intermediate, would be the oxygen radical. So my oxygen radical is actually going to cancel out. And I want to rewrite what's left over. So I would have 2, because I have 1, and then the second one, 2 N2O particles. And that's going to react to form, again, 2 N2s and 1 oxygen. And these are all gas phase. Next, they want us to write the rate law for the overall reaction. Well, for the overall reaction, I just have one reactant, but I have 2 of them. And so for my overall reaction, I would say that rate equals N2O to the second power because I have 2 N2Os that have to collide. Now, sometimes they give us information about how quickly each of these steps happen. So notice on step 1, it says that that occurs slowly and that step 2 is fast. So that tells me that step 1 has a high activation energy. So activation energy is the minimum energy needed for a reaction to occur. So if a step is going slow, that means that it must have a high activation energy. So step 1 has the highest activation energy because it is the slow step. If it was the fast step, we would expect it to have a lower energy barrier or a lower activation energy, which means that the reaction will occur much faster. Sometimes we are given information about those speeds, like we saw in the last example. And the thing that we need to know is that the slowest step is considered the rate determining step. Because it has the highest activation energy, we want to base our rate law off of the slowest step that's given to us. So in this example, I have a slow A plus A goes to B, and then a fast B plus C goes to D. Again, my intermediate is B, and so B gets used up. And my rate law is going to be based off my slowest step. Now, luckily for us, our slow step was the first step. So if I was writing this rate law, it would be rate equals K times A to the second. Again, we're basing it off of that slow step and two A particles needing to collide. And that's what's listed here. I guess I didn't need to write that. If the slow step comes later, then I would cancel up into that point. So here in the example, they've switched it and said that our fast step was first and our slow step was second. So if it occurred like this, then my rate law would be the sum of those elementary steps up until we get to the slow step. If the reaction had 3 steps and number 2 was the one that was slow, I would not add anything from reaction 3. So you're only adding until you get to that slow step. Okay, back to ozone. We have another mechanism for ozone, and we're going to answer some questions about it. Another mechanism for the conversion of ozone to O2 shows the possible destruction of the upper atmosphere by NO, as shown below. So here we have 2 steps: ozone, which is the O3, plus NO, and that's going to create NO2 plus oxygen gas. That's listed as a slow step. And then in the second step of the mechanism, the NO2 that was produced is used up with the oxygen radical, form NO and O2 gas. So they want us to write the overall equation. And I do that by eliminating my intermediate. Remember, the intermediate is the thing that gets used up first. Then I can also cancel then O. Do you guys see how the NO appears on the left-hand side and then gets regenerated on the right-hand side? We haven't quite talked about that yet, but that is actually an example of a catalyst. A catalyst kind of does the opposite of what an intermediate does. An intermediate shows up as a product first, then gets used up as a reactant. Well, a catalyst will show up as a reactant first, then will be reproduced as a product. And so that's what's happening with that NO. So I actually can get the NO out of there as well. It's not part of the overall reaction. So here I have O3 reacting with an oxygen radical to produce 2 O2s. The intermediate in the equation was our NO2. That was what was produced and then used up. And then, like I mentioned again, our catalyst is something that was a reactant and then got regenerated as a product. They didn't ask me for this, but just to introduce it here. Never mind, they do ask us about that. What's the role of the NO? It's a catalyst. And how do we know that it's a catalyst? Is because it does not get consumed by the reaction. Doesn't get consumed. If it was a reactant, it would get used up. What is the molecularity of each step in the reaction? The steps in this reaction would be bimolecular. Both of them have just 2 particles that would be colliding, bimolecular. And then finally, they want to know what is the rate law of this reaction. And we always base our rate law off of the slow step. So this is going to be rate equals K times ozone concentration times NO. concentration. All right, that's all I have for you today for 5.4. Thanks for listening, and I will see you next time.